Hi all. So in the previous video, we went through the computation of so-called hyperbolic Lagrangian covariant structures based on the variational theory. Now, the structures we were getting were associated to a finite time interval. So we're computing the corresponding repelling and attracting LCSs over some finite time interval. Now, the computation of the OECSs, so of the basically Eulerian counterparts to the LCSs, follows exactly the same principles. And in this video, we will show how to compute these OECSs, so these hyperbolic OECSs, in two different ways. One way you can compute them is, of course, using the same approach we use for the LCSs by simply replacing the deformation tensor, so the Cauchy-Green strain tensor, with the rate of deformation tensor, so basically with the rate of strain tensor. And that's the first way you can compute them. We will go through these. So the files are located in the hyperbolic OECS folder. Again, these four notebooks are so these four auxiliary notebooks are basically exactly the same as the ones from the LCS computation. And we'll again highlight our results on the sorry about that, on the Agulhas region. So if we take a look at the script, the first four steps, again, essentially the same: importing data and interpolating the velocity field. And the step number 5, so the computation of these hyperbolic OECSs, is also the same basically as for the LCS case. The only difference is that here we replace the Cauchy-Green strain tensor with the rate of strain tensor, so with this S matrix. And of course, instead of using the eigenvectors of the Cauchy-Green strain tensor, we need to use the eigenvectors of the rate of strain tensor, which are denoted as E, and the eigenvalues of the rate of strain tensor, which are denoted as SI. Now, again, for an incompressible fluid, it holds that the most dominant eigenvalue, so S2, has the same magnitude as S1, so as the weakest eigenvalue, but simply a different sign. Why? Because the trace of this tensor here needs to be 0 for incompressible fluids. And so if you sum up the two eigenvalues, they need to give 0. Again, repelling OECS and then computing as curves which are tangent to the weakest eigenvector, so to the eigenvector associated with the weakest stretching, with the highest compression. And the attracting OECS is a tensor line which is tangent to the E2 eigenvector, so to the most stretching eigenvector. And then generally you would, so again, you look for local maxima of this S1, of the SI field, actually, sorry, of the S2 field. So you call these objective saddle points. Keep in mind that since the rate of strain is an objective tensor, the eigenvalues and the eigenvectors also need to be objective. So we call local maxima of S2 also objective saddle points, and also local maxima of S2 are equivalent to local minima of S1. And so you look for these local maxima, and then you launch from these local maxima simply these repelling and retracting OECSs, and you stop the integration of these tensor lines as soon as the stretching, basically as the S2 stops to be monotonically decreasing, or as soon as it's below a certain threshold. Of course, if you launch these tensor lines from local maxima, then as you move away from these local maxima, the S2 will start decreasing. And if we go through the computation, so their scripts are essentially the same as for the LCS case. Simply we use the rate of strain tensor, and what you get, so yeah, sorry, and the parameters need to specify are also related to the integration. So these are exactly the same parameters as we had in the LCS case, and you just simply need to pass them to this function tensorlines, which is defined in the same folder, simply here. So this is the tensorlines function, which then has access to all the other functions. Now, when integrating the tensorlines, then we mentioned in the LCS case that when integrating, or when computing these tensor lines, so these lines which are tangent to a certain eigenvector field, then one of the problems is that during the integration, you always need to keep track of the orientation of the tensor line, because if you start integrating in this direction and then suddenly you get into a point where the eigenvector is flipped in this direction, so basically in the opposite direction, then the integration stops. And of course, the direction of the eigenvector is not really well defined, so the eigenvector that is returned by the eigensolver is generally arbitrary. So the orientation of the eigenvector which is returned by the eigensolver is generally arbitrary. So you need to make sure that at every point in the integration, you need to reflip the eigenvector so that it points in the correct direction, that you can continue the integration. Now, that's why we have all these. So if we go back here, we have all these sorts of functions which, for example, take care to reorient the vector field. If we take a look at this function, then if this is a grid cell and you have these, let's assume that this is the E2 eigenvector field, okay, and this is a grid cell, and you need to evaluate the eigenvector at this point here. So of course, the orientation of these eigenvectors is random. So in reinterpolating to this point is problematic. What you want to do is you want to reorient all these vectors so that they point in the same direction. What you do is you simply fix this initial vector and you take the inner product of this vector with this vector, of this vector with this vector, and of this vector with this vector. And depending on the sign of the inner product, the eigenvectors gets flipped. So for example, here you get from this configuration, you need to flip all the eigenvectors manually. And then you can continue with the integration and simply continue with the integration. Now, if you do this integration properly, then you get the following results. So here I've plotted the repelling and the attracting OECSs. So basically the black and the white. So black is attracting and white is repelling OECSs, and they are launched from these local maxima. So you launch from all these points, which are local maxima of the S2 field. So what I've plotted here is simply the S2 field. And then, of course, you get all these sets of points. Now, an alternative approach to computing the eigenvalue, the attracting and repelling OECSs without the need to keep reorienting these eigenvector fields is given in this fast Tensorline computation for us. So this fast Tensorline computation, what it does is it computes the eigenvalues. It computes the attracting and repelling OECSs on the fly without the need to check the orientation of the eigenvectors during the integration. So if we go to the main script of this fast Tensorline computation, here, how do we approach this problem? So the first 4 steps are essentially the same. What do we do then? What we need to do is, of course, we need to compute the rate of strain tensor. We need to compute the eigenvectors of the rate of strain tensor. Then, so again, the problem that we're facing now is that you wanna integrate and you wanna compute these hyperbolic OECSs without needing to check the orientation of the eigenvectors at every point during the integration. Okay. So what you do is conceptually you set up this eigenvalue problem. Okay, so this is simply a standard eigenvalue problem, and you parameterize the tensor lines. So you say that the tensor lines are parameterized curves which are tangent to the respective eigenvector, okay, EI. And you parameterize this eigenvector through the angle. So you pick the eye. So you can uniquely parameterize this eigenvector simply by specifying the angle with respect to a certain axis, right? So you plug basically this expression here back into your eigenvalue problem, and then you basically differentiate this eigenvalue problem with respect to the parameter S. When you do this, you can work through the equations, and you can then have an evolutionary equation for phi prime, where phi is simply the angle parameterizing the eigenvector, okay? And then you say that the repelling OECSs are tensor lines which need to satisfy the following set of ODEs, where the first 2 ODEs simply are related to the orientation of the eigenvector. Okay, so cosinus phi is simply the x component of the eigenvector, and sine phi is simply the y component of the eigenvector. And you parameterize the evolution of these components simply through this ODE. And then, of course, you also need to parameterize the evolution of the angle. The evolution of the angle is specified by this form here, where one of the simplifications that we used is that that the inner product between the eigenvector and the derivative of the eigenvector with respect to S is, of course, 0, because E is constrained to be an eigenvector. Is constrained to be a unit vector. Okay, so of course the eigenvectors, they are initially constrained to be unit vectors, as you can see from this form here. And then, of course, we use that the incompressibility assumption, which specifies that the two eigenvalues Si and Sk need to have the same magnitude, but with opposite sign. So the only thing we actually need to do is, again, we need to look for the local maxima of the S2 field, because that's where we want to launch the tensor lines from. And then we simply need to have an interpolant for this right-hand side. Okay. Once we have that, we can simply plug this basically into a standard ODE solver and start the integration from local maxima of the S2 field and integrate them using this formula. Of course, you need to specify initial conditions. Well, the initial condition is you need to specify the initial angle, right? And the initial angle is simply given by the initial eigenvector, right? So whenever you launch the tensor lines from the local maximum, then you have a local maximum, and there you have a specific eigenvector associated to this local maximum, right? And this eigenvector, of course, has a corresponding angle, and this will be your initial angle. And then you simply integrate these ODEs. Of course, the ODE, you have an ODE for computing the repelling OECSs, and you have an ODE for computing the attracting OECSs. The first part of the ODE is the same. So you can see that this equation 8, 9 is the same as equation 11, 12. However, the evolutionary equation for phi prime is different, because for the repelling OECSs, you have, so they are different, but you just need to flip so here you have E2 and here you have E1. And the same thing happens here again. You have here E1, here E2, here E1, and here E2. So it's fairly straightforward if you go through the derivation of it. So that's basically it. We need to find tensor lines, and then we need to solve this ODE with the appropriate initial condition to get the tensor lines. So to get the corresponding hyperbolic OECSs. If you do this, so one crucial step here is that you need to come up with an interpolant for the right-hand side of these equations, right? So you need to basically find an interpolant for phi prime. In order to do this, you need to have access to the gradients of the rate of strain tensor. Okay, so that's a bit, that might seem a bit problematic, but you simply need to evaluate this expression, have access to the gradients of the rate of strain tensor. That's why what we do is we compute the rate of strain tensor for each initial condition here. So actually, if you take a look at the shape of the rate of strain tensor, then again, the shape of this rate of strain tensor is of course, the first two dimensions are 2 and 2, simply because it's a 2D field. So the rate of strain tensor is a 2 times 2 matrix. And then this specifies the ny, and this specifies the nx component of the mesh grid. So basically, you have a rate of strain tensor for each initial condition. And then since you wanna be able to compute the derivatives of this rate of strain tensor, what you do is you need to interpolate each individual component of the rate of strain tensor. So what we do here is we extract the S11 component, the S12 component, and the S22 component of the rate of strain tensor. Where, of course, so we don't need to extract the S21 component because the rate of strain tensor is a symmetric matrix. So S21 is the same as S12. We evaluate, so we interpolate simply the components here so that we can evaluate them at arbitrary points in space and time. And we pass these functions then finally to this phi prime function. Sorry, to this to this phi prime function. Well, we have one interpolant for the attracting and one interpolant for the repelling. So interpolant phi prime simply returns the interpolant for the attracting and the repelling evolutionary equation of the angle phi prime, of the angle phi. Once we've done that, we need to find the objective saddle points. And then, of course, you need to specify a minimum distance between the saddle points and also a hyperbolicity measure. So that's basically the measure. So, of course, if you integrate away from the saddle points, from this local maximum, then the rate of attraction or rate of repulsion will decrease. And you set a threshold on that so that once it's below a certain value, you just simply stop the integration. So here you just simply find the local maxima of the S2 field. Then, of course, we need to compute the initial conditions. So x0 and y0 simply are the locations of the local maxima, and phi0 is simply the simply the angle of the eigenvector at these local maxima. Okay. And of course, here you have an angle for the attracting and an angle for the repelling, because you wanna integrate. So you know by construction that the E2 vector, so the most stretching direction needs to be orthogonal to the most compressive direction, and that's why the initial condition for the repelling and the initial angle for the repelling and the initial angle for the attracting OECSs need to be different by 90 degrees. Okay, and then you simply compute the attracting and repelling OECSs by using an appropriate ODE solver, which we do here. So here we simply plug. So this is just like so this is the ODE solver I implemented, which I called extract hyperbolic OECSs and extract hyperbolic. So sorry, this is the ODE solver, which simply solves this initial value problem. This ODE solver returns the repelling and attracting OECSs. And that's pretty much it then. So one can then plot these repelling and attracting OECSs. And again, we would expect that the repelling and attracting OECSs we get from the fast tensorline computation are the same as the one we get from the classic tensorline computation. So from this tensorline computation. And you see that if you compare the two structures, they are exactly the same, right? Again, the fast tensorline computation, we call it fast because it doesn't require to check whether it doesn't require to check the orientation of the eigenvectors as you do the integration. Now, of course, the dimensionality of the integration is increased a bit because here, so this ODE has much more dimensions, so it has this additional dimension of the angle. However, it does not need, so it's a pretty straightforward standard ODE integration, and you don't need to manually check at every point in integration the orientation of the eigenvectors. And if we analyze the results, so that's the field and the hyperbolic OECS that we get, one can then proceed by advecting these OECSs and seeing what kind of effect they have on the nearby material distribution. So basically, what I did here is I placed material elements around local maxima. So these the red indicates basically the inner core, and the blue indicates the outer core of these material elements. And I would expect that as I advect them over some fairly short intervals, these attracting OECSs, which I have here, will attract and stretch these material elements along these black curves. And in fact, that's what's happening. So here I did the simulation for up to 1.5 days, and you can see that an initially perfectly circular material element will get stretched significantly along the so-called attracting OECSs, or also stretch lines. With that, I would like to thank you for your attention, And in case there are any questions on the implementation or on the theory behind this, then just simply feel free to contact me.